Building heat protection is a comprehensive building design measure to reduce the effect of outdoor heat in summer and prevent indoor overheating. Overheating of the room will lead to the deterioration of the thermal environment. The thermal comfort of the human body will deteriorate, and the energy consumption of air conditioners will increase. Therefore, building heat protection is also an energy-saving design. The hot and humid climate is characterized by small daily temperature difference, daily amplitude below 7 centigrade, high humidity, and low wind speed. These characteristics are not conducive to natural ventilation. Therefore, it is necessary to strengthen the effect of natural ventilation through architectural design methods. The hot and dry climate is characterized by strong solar radiation, large daily temperature difference, and daily amplitude above 7 centigrade, and low humidity, which seems to be conducive to nighttime ventilation. However, the use of natural ventilation is also limited due to the hot wind and the large sandstorm, and the dry characteristics allow us to use evaporative cooling. Therefore, the contact air between air and water can be increased through architectural design methods, and horizontal ventilation can be charged to water ventilation. From this, the design principles of building heat protection are introduced. Hot and humid airs from the perspective of preventing excessive solar radiation and using natural ventilation, the orientation, spacing, and outlet that are conducive to natural ventilation should be considered. At the time, it is necessary to consider the thermal effect of the external environment on the building. Adjust the temperature and humidity of the external environment through greening. Reduce the thermal radiation of the external environment to the building, and cool the air inlet through the window shading and the heat insulation of the outer protective structure. Prevent the influence of solar radiation on indoor thermal environment. Strengthen natural ventilation by determining a reasonable height of the window sill, such as setting the height of the window sill in the bedroom close to the height of the bed, using floor-to-ceiling windows in the living room, and setting window seats to prevent solar radiation from entering the room during ventilation. In addition, we must also pay attention to the needs of moisture-proof, rain-proof, mildew-proof, lightning-proof, insect-proof, etc. Generally adopt the low-level overhead form. In dry and hot airs from the perspective of preventing solar radiation and hot sandstorms, heavy building materials are used for heat insulation and heat storage. The building forms that are closed outside and inside are used to prevent sandstorms and ventilate, and measures such as pools and water storage roofs are used to cool down. Using wet scan and densely arranged buildings to reflect the solar radiation and mutual shading. Passive measures refer to cooling the building by relying on the thermal performance and adjustment ability of the envelope structure itself, such as window shading, natural ventilation, heat insulation of the envelope structure, and the grating environment. Active measures refer to relying on equipment to cool the building, such as air conditioning, mechanical ventilation, etc. There are 4 reasons for indoor overheating. The first is the heat transfer from the envelope to the interior. The second is the heat from the incoming solar radiation. The third is the heat brought in by ventilation. The fourth is the residual heat generated in the room. Building heat protection is to reduce the amount of outdoor heat entering the room, and the indoor heat to be dissipated as soon as possible. The heat protection design should be comprehensively dealt with. Instead of taking measures alone, merely using heat utilization and natural ventilation, supplemented by window shading and greening. The principles of thermal insulation design of the outer envelope structure are: the first, determine the insulation site. The focus is on the roof, followed by the west wall and the east wall. This is considering the solar radiation intensity and sunshine hours received by the outer surface of the outer envelope structure, which is the largest horizontal plane, and second in the east-west direction. The second, take measures to reduce the solar air temperature. Use light-covered and smooth stucco and finishing materials for the outer surface of the structure, as well as materials with low absorption of solar short-wave radiation and high long-wave emissivity, such as roofs with white ice covering, to reduce the absorption of solar radiation. Set up shading facilities on the outside of the roof or wall. The third, set up ventilated inter-air inside the outer protective structure, such as ventilated roof and ventilated curtain wall, using weak pressure and hot pressure to take away the heat in the air there, thereby reducing heat transfer. This method is very suitable for natural ventilated rooms that require good heat insulation during the day and fast heat dissipation at night. The first, according to the climate characteristics, room function, and structural position, the thermal insulation capacity of the outer protective structure is reasonably selected. For areas that are hot in summer and warm in winter, it is required to consider both heat insulation and heat dissipation, such as the use of ventilation envelopes. For areas with hot summer and cold winter, it is required to consider thermal insulation. Due to the requirements of room temperature stability and energy saving, the heat transfer coefficient of air-conditioned room is lower than that of natural ventilated rooms. The fifth, using the evaporative cooling effect of water and the transpiration effect of plants to cooling buildings, such as water storage roofs, water spring roofs, earth-covered roofs, and planted roofs. Climbing plants also have the same effect. Think about it. What areas are suitable for water storage roofs and planted roofs? Are there any special requirements for this method? Are there any downsides? Due to the need to consider frost protection, this method is only suitable for warm areas. Due to the need to consider the weight of water, soil, and plants, this method increases the structural load and puts forward high requirements for root blocking, waterproofing, and insect control. Although the water storage roof has a good heat insulation effect during the day, it is difficult to use the roof to dissipate heat at night due to its strong heat storage capacity. The sixth, the thermal insulation calculation is carried out according to the thermal insulation design standards to ensure that the maximum temperature of the inner surface of the outdoor envelope structure is lower than the local maximum outdoor temperature. The seventh, make full use of natural energy. The thermal insulation structure of roof mainly includes solid material there and thermal insulation roof with closed air there, thermal insulation roof with ventilated inter-air and attic roof. The solid material there and the thermal insulation roof with the closed air there should be made of material with low thermal conductivity. At the same time, attention should be paid to the arrangement order of the materials. Different orders will lead to different attenuation of the structure. The choice of the material and color of the outer layer should be helps reduce the absorption of solar radiation. The thermal insulation effect of a ventilated roof mainly comes from the heat taken away by ventilation, and the air motive force includes wind pressure and thermal pressure. Therefore, the ventilation opening should face the prevailing wind direction in summer, and the surface layer of the interior can be properly extended at the cornice. The thermal insulation effect of a ventilated roof is significant in wet areas. When using a ventilated roof in a low wet air, the height difference and temperature difference of the air inlet and outlet should be increased to utilize thermal pressure ventilation. The height of the interlayer is not as high as possible. It should be 20 to 24 cm. The lower limit of the pitched roof can be taken, and the upper limit of the flat roof can be taken. In order to ensure the ventilation effect, the inner surface of the interlayer should not be too rough, and the area of the air inlet and outlet should be larger than the cross-sectional area of the interlayer. This is the air organization form of the ventilated roof. The weight pressure used in Fig A, the heat pressure used in Fig B, the weight pressure and heat pressure used in both indoors and outdoors in Fig C. In order to increase the heat pressure, an exhaust cap can be installed in the middle of the horizontal ventilation roof to increase the heat difference between the air inlet and outlet. And the top of the cap is painted black to increase the temperature in the exhaust cap by enhancing the absorption of solar radiation. The ventilation forms of the ventilated attic mainly include openings on the gables for ventilation, air enter from under the eaves and exhaust from the roof ridge, and dormer windows on the roof for ventilation. The natural energy that can be used in building thermal protection design mainly includes solar radiation, effective long-wave radiation, nighttime convection, water evaporation energy, and ground cooling energy. Solar cooling refers to passive shading. Passive solar cooling uses the shading effect of solar thermal and photovoltaic device to make the building in a shade air, while solar air conditioners are active cooling. Night ventilation belongs to convection heat transfer. Research has found that the cooling effect of continuous natural ventilation throughout the day is not as good as intermittent natural ventilation. When it is semi-continuous in summer, in a room with continuous natural ventilation throughout the day, the indoor and outdoor temperature are basically the same during the day. The average daily indoor temperature is 1 to 2 centigrade higher than the outdoor temperature, but it is about 3 centigrade higher than the outdoor at night, indicating that the continuous natural ventilation does not really achieve the purpose of cooling. Ventilation at night belongs to intermittent ventilation, and natural ventilation or mechanical ventilation can be used. By closing doors and windows during the day, the extraction hot air can be avoided, the rise of room temperature can be restrained, and the heat storage of building envelope can be reduced. At night, dry and cool outdoor air is induced to remove indoor waste heat. It can be seen from this table that in areas with a daily difference greater than 7 centigrade, the effect of nighttime ventilation is very good. The average indoor temperature and maximum temperature are significantly lower than those of the outdoor, and the effect of mechanical ventilation is better than that of natural ventilation. Ground source air conditioners use the principle that the ground temperature in summer is lower than the outdoor air temperature, and the outdoor air is induced into the ground to exchange heat with the soil and cool it down, and then send it into the room. Compared with the natural ventilation, the room temperature is lower and more stable, and the investment is low. Passive evaporative cooling is a method of using the latent heat of evaporation of water to reduce the temperature of the exterior surface of the building, thereby improving the indoor thermal environment. Mainly use water storage roof, water spraying roof, or paint hygroscopic material on the outer surface of the building, and laying porous moisture container material on the roof. Long-view radiation cooling is the use of nighttime radiation to cool down. It is suitable for areas with large temperature difference between the day and night. In order to achieve better cooling effect, the building skin can be treated with light color and painted with selective radiation paint. The energy-saving design of air-conditioned buildings should pay attention to the following aspects. The first, reasonably determine the indoor thermal environment standard for the air-conditioned buildings, and the premise of satisfying function. Generation-saving building can appropriately reduce the indoor design temperature in winter and increase the indoor design temperature in summer. The second, reasonable design the building plan and shape. Improve the external environment by increasing the greening and water surface around the building. Use as small an outer surface as possible. Avoid long and narrow slider and too much convex and concave. Give priority to north-south orientation and try to avoid east-west orientation. Arrange high-pressure air-conditioned rooms in general air-conditioned rooms as much as possible. Arrange air-conditioned rooms in non-air-conditioned rooms and avoid arranging air-conditioned rooms on the top floor. Arrange the equipment room close to the air-conditioned room, which can reduce the energy consumption of transportation. Outer door is equipped with air partition measures, which can be closed entrance ports, revolving door, automatic door, air curtain, etc. The third, improve and stress the thermal performance of envelope structure. The fourth, window insulation and shading. Reduce window air and shade. The thermal insulation performance of window is improved by adopting measures such as dot-layer glass, ceiling strip, thermal insulation curtains, heat-softening glass, and coated glass. The fifth, linkage control of thermal environment of air-conditioned rooms. The leakage control composed of natural ventilation adding fan adding air conditioner is to ensure comfort and energy saving by controlling indoor temperature and wind speed at the same time. When the indoor temperature is lower than the outdoor temperature, it is naturally ventilated, and fan is turned on when the outdoor temperature rises and does not meet the thermal comfort. When the indoor temperature is equal to the human body surface temperature, close the window and turn on the air conditioner. You can try to analyze the physical buildings according to the above principles and methods and see if the school buildings have adopted heat protection and energy-saving measures. Do the buildings in your hometown comply with the principles of heat protection? How to apply heat protection measures in architectural design work?